Okay, this lesson is on special functions. We are going to be identifying and graphing absolute value in piecewise defined functions, and I'll show you what that means in a second. Piecewise linear functions are literally pieces of lines, so it might look like something like this. So this would be a piecewise linear. If you have like a line segment, or not a line segment, array going one way and another one going the other direction. That would be a piecewise linear because they're pieces of lines. An absolute value function is shaped like a V because the part of the line that would normally, if it was linear, go this way, if it continued along that, is flipped up over the x-axis so that it's not a negative value. Well, I'll explain that in a second. Piecewise defined could be any pieces of any functions put together. So the first one is piecewise linear. It's pieces of a linear function. Piecewise defined could be pieces of a quadratic function with a linear function. Okay, so as I said, an absolute value function is shaped like a V. And its domain is all reals because it's going forever to the right and to the left, like that. So its domain is all real numbers. The symbol for all real numbers is the R with the line through it. And its range is all negative, non-negative real numbers. So if this was the graph that we were asking about, its range would be, remember, range is all the y values. So y is greater than or equal to 0 because 0 is the lowest y point and it's pointing upward. So now I'm going to show you how to graph an absolute value graph. So we're graphing f of x equals absolute value of 2x plus 2 and then stating the domain and range. Well, you know that absolute value is the distance away from 0. So it cannot be negative. What's inside the absolute value can be negative, but it cannot equal a negative number. So the first thing that you're going to do is you're going to set everything inside the absolute value signs equal to 0 and then solve for x. That will be your center x value on the xy table of values. So for instance, if you have, I said set everything inside the absolute value, so everything inside the value is the 2x plus 2. Set that equal to 0 and solve for x. So I'm going to subtract the 2 and then divide that 2. So I would get x equals negative 1. So on a table of values, I'm going to put that as my center number. And then I'm going to think about what is one number less than negative 1, be negative 2, and one number greater than negative 1, so 0. You're going to put those values, so that was our center number. Okay, you're going to put those values that I have for x into the original function right there. Okay, so if I do that, I would get 2, I'll do it up here. I would get the absolute value of 2 times negative 2 plus 2, which is the absolute value of negative 4 plus 2. The absolute value of negative 2 is 2, so that value goes right here. If I plug a negative 1 in, oops, wrong thing. If I plug a negative 1 in, I would get 2, the absolute value of 2 times negative 1 plus 2. So that would be the absolute value of negative 2 plus 2, which is absolute value of 0, so I get 0. If I plug a 0 in, 2 times 0 is 0, plus 2 is 2, and the absolute value of 2 is 2. All you have to do now to graph this is draw your graph, plot the points. So negative 2, 2, negative 1, 0, and 0, 2. And then graph your line just like that. And that's not pretty, but it's the right graph of absolute value graph. And you would say your domain, remember, is all reals or all real numbers. And your range, what is your lowest y coordinate? And so that's 0, right? Because this is the lowest point and it's going up. So you would say y is greater than or equal to 0. This is the same thing, but theirs is much prettier. I don't like how they have the range is all non-negative numbers. I would much rather you put that the range, the domain is all reals and the range is y is greater than or equal to 0. Okay, I'm going to give you a second to go ahead and graph that and then state the domain and range. And this is the answer that you should have gotten. One thing that's important when we're graphing absolute values is transformations. You have done transformations. You did transformations when we graphed quadratics. You've done transformations when we did linear. You've done some transformations when we did exponential functions. And now you're going to do the same kind of transformations, but with absolute value graphs. Okay, so remember vertical stretch and vertical compression, x-axis reflection, and horizontal and vertical translations. So let's look at this first one. The 2 in front, right there, means that is a vertical stretch. Now, you don't have to do all this to be able to do this section, but it is helpful when you're doing a standardized test and you have to do it quickly. The -5 inside the absolute value graphs means that you're going to the right 5. And this +3 is on the outside, so that means you're going up 3. So if I was to sketch this first graph, I would first go to the right 5, up 3, and then that would be where the center point of my absolute value graph is, and then stretch. That 2 means that I'm going up 2 and over 1 in either direction. Now, do you have to be able to figure that out? No, but it's very quick if you can. Okay, the second one, the negative sign in front means an x-axis reflection. The 1/3 means a vertical compression. The +2 inside means that you're going to the left 2, and the -4 out to the side means that you're going down 4. So what would that look like? My lovely straight lines over here. Okay, so let's go to the left 2, down 4. That is my center point. It's an x-axis reflection, so I know it's pointing down, and it's a vertical compression, so I know it's wider. So it's like I'm going down 1 over 3. So it actually would be about like this. If I graphed it, it would look something like that. So let's graph this problem using the points like we did in the first example, because really that's what you're going to be doing most of the time. So you take what is inside the absolute value, which is just the x plus 2, set that equal to 0, and solve for x. So you get -2. So in your table, that number goes in the center. So what is one number less than -2? -3. What's one number bigger than -2? -1. So we are going to, and I just want to put this here so you know that's where I got those numbers from. Okay, so you're going to plug those numbers into the original function. So I'm going to go, f of x is the same thing as y, right? It's just function notation. So I'm going to plug these numbers in one at a time. All right, so order of operations, -3 plus 2 is -1. What is the absolute value of -1? 1. 1/2 minus 3 is negative 2.5. Now I'm going to plug negative 2 in. So I've got, I'll do it in a different color. So I've got y equals 1/2. I'm going with the original function again, just plugging in these numbers. Negative 2 plus 2. Whoops. Okay, so y equals 1/2. Negative 2 plus 2 is 0. The absolute value of 0 is 0. Anything times 0 is also 0. 0 minus 3 is negative 3. Now, I am not going to work this one out. I want you to pause the video and see if you can plug negative 1 in and see what you get. Okay, you should have gotten negative 2.5. So now we're going to plot those points. You've got 1, 2, 3, 1, 2, 3. Now this is hard because first it's my graph and they're not spaced out perfectly. Okay, so negative 3, negative 2.5, negative 2, negative 3, and then negative 1, negative 2.5. But you can see I want to make that straight as possible. There you go. And there you go. So does that follow in line with what we learned about transformations? It should be going to the left 2, down 3, and wider, and that works. If I ask you what the domain and range for this would be, you should say the domain, of course, is all reals, and the range is talking about the y. So what is the lowest y value? It's right there. Y is greater than or equal to negative 3. All right, now we're doing piecewise defined functions. So what this means, it says graph f of x equals negative x if x is less than 0, and graph f of x equals negative x plus 2 if x is greater than or equal to 0. Now I know this looks kind of weird to begin with. All right, but it's not that bad. What this actually means, this first one, is the same thing as saying graph y equals negative x. And the second one is the same thing as saying graph y equals negative x plus 2. So I'm kind of going to do this on this smaller graph and then let you see how it transforms to piecewise on the other one. Okay, so if I was just graphing these two graphs, y equals negative x, you would start at 0, 0, and your slope goes down 1 over 1 in both directions. So if I can draw a straight line, that would be fabulous. That line would look like this. Now, if I graphed y equals negative x plus 2, you would start at 2 and go down 1 over 1. And so this line, again, if I can graph it straight, it's pretty good. Looks like that. Okay, so that's what those lines would look like. Now, when they're piecewise, the domain is restricted. Okay, so right here, this part, that is called the domain restrictions. So it's the same graph, but you only graph part of it. It's the same line, I'm sorry, but you only graph part of it. So this red line, the y equals negative x plus 2, that's only true where x is greater than 0. So you plot your points again. So you go up to 2 and down 1 over 1, but you only graph that line where x is greater than or equal to 0. Because it has greater than or equal to, it's going to be a solid circle, just like you would do on a number line, and you only graph the part of the line that's greater than or equal to 0. For the blue line, again, you start at 0, 0, and you would go down 1 over 1 or up 1 over 1 backwards. But you're only graphing this where x is less than 0. So I'm going to have a big open circle here, and I'm only going to graph the part of that line that is less than 0. So I would get rid of the other little blue dot because I don't need it because it's not less than 0. So you can see these are the two same lines. The difference that makes it piecewise is that I'm only graphing pieces of the lines because of those domain restrictions. And this is what it looks like. Very nice. The domain is all real numbers because you're not missing any x values. This continually goes from the left to the right. Even in the middle where there's a break in the graph, it still hits all of those x coordinates, and the range is the same. It goes from the bottom to the top without missing any y coordinate. All right, so I wanted to try one more before giving you one on your own. All right, so let's just graph y equals 3x plus 4. I feel like y'all are competent in graphing lines. So this first one right here is going to be the same as y equals 3x plus 4. So you would go to 4 on your y-axis and go up 1, 2, 3 over 1, 1, 2, 3 over 1. You could also go down 1, 2, 3 over 1 this way. Now, the domain restriction says if x is greater than 1. So what I'm going to do, just imagine that there was a line here, okay? Well, I think I can do a backspace on this thing. So imagine this line looks like that, okay? But I only need the part of the line where x is greater than or equal to 1. So anything that is less than 1, I don't need. So I can literally erase that line. That's perfect, actually. And that's going to be a solid circle. Why is it a solid circle? Because it's greater than or equal to 1. So that's going to be a solid circle. All right, the next one right here, I am graphing y equals x plus 3. So you would go to 3, and then you would go up 1 over 1. Because my slope is 1, you can also go down. All right, and then we're going to graph that line. But this domain restriction says if x is less than 1. So I don't need anything greater than 1. So I'm going to erase all the stuff where x is greater than 1. I stopped where x is equal to 1. And now I need an open or closed circle. An open circle because it says it's less than 1, which means I'm not including that point. And that is my graph. Now let's look at the domain and range. Okay, so my domain, am I covering all the x coordinates? Yes. So my domain is going to be all reals because even where x equals 1, where it stops with the blue line, it picks up with the black line. Your range, on the other hand, has a gap. Can y'all see that? Your range has a gap right here. There's nothing there. Okay, so I'm going to say that my range is y is everything less than 4, and it's also y is greater than or equal to 7. So that's it. My range is everything that's less than 4 and that's greater than 7. Okay, now you get to try one. Take a minute, pause, graph this function, and then state the domain and range and choose the correct answer. So you do have to graph it and then state the domain and range and see which one it is. Okay, this is the answer. If you have questions, you can always send me a reminder.